Hello, students. You might hear the background noise here of a 3D printer while I'm making this. Trying to keep these things running. We're doing a service program out of the business school, making some mask extenders for healthcare people. But let's get on with it here, okay? So here's the quickest review, okay? It's going to be really direct. First of all, follow the book, okay? So we used examples out of the book. That's plenty to work with here for the CPM/PERT Part 1 part of the final that we'll be having tomorrow. Okay, so let's talk about the statistics. I'm going to go right exactly to what we need to know about this. Okay, so let me get myself a pen. Always, for normal distribution work that we're doing, draw a normal distribution. Okay, and by pushing and moving numbers around in normal distribution, we get to know it. Okay, so it's not linear. It's not like you don't want to memorize an image here. You want to be working it because we have real world problems. The numbers come from that. Don't get trapped by continually seeing a curve that we keep looking at here. The data has to be meaningful to you. Okay, so let's talk about CPM PERT. Okay, so I'm not even editing this thing. I'm not even going to take my coughs out of this one. That's what takes all the time. So the two things we need to define the normal distribution are the mean or the average. Okay, so we'll call it X bar with a bar over it. And the normal distribution has a characteristic of your data will have a characteristic standard deviation. And it always appears in a perfect curve. If we draw a curve of perfect data here, the plus and minus one standard deviation occur here, two occur here, plus and minus three occur out here, right? Really fast review. Okay. What's the empirical model? We know that 68% is contained between plus and minus 1%, 95 and change, but we'll use 95%, is contained between minus 2 and 2. And finally, 99.7 of the area of the curve is contained between minus 3 and 3 standard deviations. This is the empirical model. If you walk around and have these memorized, you can remember by way of the characteristics of a normal distribution that one, it has central tendency. Most things happen around the mean. That's the height of the curve, represents how often these numbers around X occur in the population. It's very high there, and it trails off to the tails. Two, symmetric. We use this day in and day out. I'm not even sure if I'm spelling that right. It's late at night here. Symmetric. Okay. And then finally, three is that we're always looking at the area, total area under the curve is 1.0. Okay. So that gets us started keeping in mind PERT and statistical process control. Okay. How did we get those numbers? There's three key formula in Excel. Norm, dot, dist, takes your point of interest, the mean, your standard deviation, and true. Okay, so this is almost a proxy for the z value. But what it does is it calculates as your z value. But what does this shoot out of it? This shoots out the probability. And normally, if we do it by hand, it's broken down into two different processes. We have a z table here with the coarse measures here from 0 to, say, minus 3. Okay, that's a z value that we have here. And your probabilities are in here, only they're expressed as 0.xyz. Okay, so we have this table. So here's the coarse, as in COARS, the coarse z value to the 10th, 3.0, 0.0. And along the top here, we go to 0.0. We add in the hundredths number. Okay, that's why it's a matrix here. So you find your coarse number. If you need 1.61 or negative 1.61, you find negative 1.6 here, and you go to negative, you add or subtract, whatever way you want to look at it, negative 0.01. So that would be this area of the curve. And what we come out of there is with a point xyz. All right, so we come out of there and we can express that as xy.z%. Okay, that's what we've been doing here. All right, but in Excel, we actually use the norm dot dist of the three numbers that we use to compute z. There's z. Z, if we need to compute it, is x of I minus the mean divided by standard deviation. And we're taking the distance from the mean of the point of interest, and we're putting it in terms of how many standard deviations is that. And we take it over to our table here. Okay, so this is old school, all right? And now you probably on your phone can get this very quickly. So we have three equations. That's the one. Okay. Now, suppose you do have the z. That's equation 2. It's norm dot s dot dist of z true. Okay. And then finally, so that both of these give us percentage. Okay. Both of these will give us a percentage. So norm.s.dist is like the partial solution that norm.dist gives us. Okay. This is what, like, we've already calculated z out of these three numbers, right? And then finally, what happens if we have a percent out of the table? We need to relate it back to a z. Okay, let's figure that out. It's a norm.s.inverse of your probability. Okay, so those are the three major equations that make you pro analysts when it comes to looking at problems at work. Most things that you're going to encounter have some kind of variable output on this. All right, so it's not deterministic. Okay, it's not deterministic. It's stochastic. Okay, so you paid for the big words. Where'd it go? Did that just close on me? How rude. Where did that go? Please stand by. Okay, so weird things happen late at night when you've been running your computer, lots of Excel. Major day for me is Mondays. Here we are, and it is 11:15. Okay, so I'm trying to help you out with this final that we got jammed up with tomorrow. All right, so those are the three equations. All right, so here what would happen is if we're saying, we're going to get into this, what's the probability? Okay, so remember what we get out of what we're talking about so far is single tail analysis using this normal distribution. Okay, what we're talking about is picking some number x of I. Change colors here. Here's your mean. Okay, so we might pick x of I here. We might pick x of I here. Anywhere along here. Just using x of I there. X of I is less than the mean. Okay. And what we're really interested in, what we exploit the properties of normal distribution and the analysis that we're handed in this nice little kit, as long as we have the mean and the standard deviation that defines our curve. And the only thing that we're interested in is playing around with what's the point of interest regarding this set of data, the characteristic numbers of your mean and your standard deviation here. What's the probability up to and including that number? It's the area all the way. It's all the points below it, including the point we're interested in. And we do this on purpose. Okay, so we're learning a lot of ways to use this, like PERT and statistical process control, all day long. Okay, so this is like an everyday skill that we have. All right. So what happens if we have the probability and we say, what's the probability of getting a project done? Okay, let's say the mean is 39 days. What's the probability of getting it done in 42 days, given that we already know the standard deviation and we know the mean and the standard deviation here, okay? These are what we need to do to characterize it. When we have these three things, we can figure out the probability that, for instance, we don't exceed 42 days. So 42 is our x of I, okay? It's the point of interest there. Okay, but what happens if we say we want to know what is the number of days associated with a policy that says we have to be correct 95%, 9.5 times out of 10 or 19 times out of 20? When we do this, we're correct, and we just allow for the fact this is what we're to live with. The compromises in this world. We understand that we're in a stochastic, probabilistic world here, and we have a random variable. We're not going to be correct all the time. The best we can do is name what we're after. So if we want to come from the table here, we got to find 0.95, and we cross it out. We come out, we cross-reference it out. to some number. Now we know 95 is greater than 50, so it's going to be in the positive range. And if you're on top of it, you'll know that when we were talking about our empirical model, 95, this is 1, 2, 3 standard deviations. 95 correlates with 2 standard deviations. Right there, you're going to find 0.95 in the table. All right. So we use norm. So when we use Excel, we use norm.inverse of 0.95, and that's going to give us a z of 2. Okay. Okay. And just keep in mind, usually we're asked, what is the point of interest when we already know the mean and we already know the standard deviation? Put a little check mark there, right? So we're trying to figure out what day, like what's the number of days associated with 95% confidence. All right. So now we're going to have we'll have figured out with that we were given 0.95, so we can figure out norm.s.inverse will give us the z of 2. Okay, so we'll know z is equal to 2 is equal to x of I. We know the mean, and that's an x, and we know our standard deviation here. So we just solve. So it's 2 standard deviations plus x is equal to xi. That's all we do. All right. That's all we've been doing for the last 2 weeks, 3 weeks of this work. All right. But here's the 3 equations for those purposes. All right. So let's now move on. We all started in the book. If you understand the book, you will do fine on the exam. All right. So here is the set of activities and their dependencies that we began with in the CPM world, and then we carried it the same network that we have here. We carried over into the PERT world. You just have to remember how to draw this. You have to get this drawn correctly, right? So A is the beginning. It has no predecessors. Right? Then we draw B, and it depended on A. Here's A, okay? C, hey, C depended on A, right? So be able to draw these things out, okay? And be able to do early start, early finish, early start, early finish on each of these. So early finish here will carry over to early start. Okay, we're doing this so methodically. It's actually so slow that I keep trying to help you not lose the forest for the trees. That if I just asked you, you'd probably be able to figure half of this out anyway. This is nothing special. It's just figuring out the sequence of what happens. So if you look at, just to go one more level deeper here, so test prototype of D is dependent on B. Okay, so just you'd have to draw that circuit. And guess what? Here I am. I'm showing it to you right here. Stop and study this. Okay, so let's get this out of the way. Okay, let's get this out of the way and get on to PERT because we're going to use the same network. Get this fancy box here. Throw that over there. Throw that over there. Okay, so I'm showing you what we did in class here. Okay, so now in PERT, we have, hold on a second, I have to bring it up to the top here, is bring to front. Okay, so this is, follow the book, and you're going to get the exam right. So here we have, they said just refer to what the CPM relationship of these were, but we have the optimistic, we have the pessimistic, and we have the nominal value for each of these activities, right? So how did we calculate that? Okay, so here I just had given you this framework. Okay, so what are the steps involved? All right, so just remember, we're dealing with this. I'm going to draw a tiny one here. Standard deviation here. You need the mean. You need the standard deviation. Okay, here's the mean right here. Tells you the pancake recipe. A little egg, a little flour, a little milk. 1A, one of the optimistic, plus 4 flours or 4 nominals, plus the milk, one of milk. You have a total of 6 units, so you divide by 6. That's the weighted average. So the first thing you have to do is just use that equation and use these numbers and calculate it out. Okay, so you're going to calculate them all the way down, and then comes the fun part. You've drawn the network. Okay, Q network. Where's the network? Thought I brought that in here somewhere. Hold on. Okay, I forgot where I put it. It's hiding. Okay, not on purpose, but anyway. Let me just get that and get that. Okay, try that again. Escape. Try this. Get that, and I'm going to group it together. Group it together. Get me out of there. Okay, so there's the network. This is straight from the notes when we were doing this in class. All right, so here is your optimistic, nominal, pessimistic. We calculated the means here. Whoop, that's a screenshot. Okay, so we just used this equation right there. This is us running the equation out. This is a screen grab. I can't show you the formula in there. That's the formula right there. Okay, so we run this out and we plug all the numbers into the network that we already figured out. So that's the network. That's the shape of the network right now, right? So now we're using these new computed numbers, right? We have 21 in here for A, B is 5, C is 7, D, and we go through there and we just plug the numbers and what do we run? We run early start, early finish analysis. That's across the top of this, right? Across the top of the circles, we have to figure out, especially when it bifurcates here, okay? It's actually when it actually condenses, okay? So when we're going through the early start, early finish analysis, when we have a, what do we call it, confluence, the confluence of two events come into F, two activities come into F, notice D and C, that's the decision point. Okay, so remember, we're trying to figure out what the longest path through here is. We have one northern route, we have one mixed route through here, all right, sort of north to begin with, drops to the south. We have one from the south that goes to the north. And then we have finally one along the bottom. So there's 4 paths in here, okay? So we plug in our numbers, early start, early finish for all these things, okay? And so remember, when you're going to activity that has 2 feeding it or 3 feeding it, you always take the higher number because that means that activity is finishing the latest, all right? So the ensuing activity or the following activity has to wait for the longest predecessor. It has to wait around for that and that's the early start. It's early start. We can start. So we go all the way through and we find out that we come up with 38 days. We have our mean, folks. We have our mean. So we be careful here. Do not add all these numbers together. You're just adding the critical path, which is marked in whatever color that is. I have no idea. All right. All right. So we did it by hand here as 38, and then we went back and we just ran a sum only on the critical path. Right. Okay. So now things get interesting. We need standard deviation. Well, we're given an equation for variance. Use a color since I have colors. I'm going to use green. Okay. All right. So now what we know is we can drop back and we don't have to analyze the variance for all or every activity, only the critical path now. Okay. Because we're going to come up, crooked pad, we're going to come up with what? Let's start drawing it. We already have 38 days we figured out. Now we have to figure out standard deviation. How do we do that? Well, we have an equation for variance. For every individual activity, we take the pessimistic minus the optimistic, that's the range, divide it by 6 because we're told so. Nothing to think about there. We're just told use this equation. All right. So 1/6 of the range and square that. Okay. So we did it only for the critical path activities and we sum them up down here. Same thing. Don't add all of these up. If you calculate these, make sure you don't add all these up. All right. So who's going to guess what to do with the variance to get to the standard deviation? Well, of course, you're going to take the square root. It's telling us to do that, right? So we get our standard deviation. Yay. Okay, so there's a standard deviation. 1, 2, and 3 out. Get used to writing that out there because we're just making that a standard approach to this. Use our empiric. We can rely on our knowledge of the empirical model here. Okay. All right. Boom. We've got everything we need. 38 comma, standard deviation is, hey, let's calculate it. I believe these numbers are fairly, it's going to be approximate possibly, okay? So I don't want to move that because it's a screenshot. I'm going to do it up here, okay? So what is the square root SQRT of 11.9? So we might end up with a little bit of loss of precision because that's probably just showing 11.9. It's probably many more digits than that, or possibly more digits than that. Okay, so we're going to take that. And what is this telling us? It takes us 38 days to get through, and on average, plus or minus 3.45 days. Like, let's just say 3.5 days, right? Okay. Okay. So on average, the part of our model here, okay, okay, our average was 38 right here. Okay, so remember, 50% of the curve below, 50% of the area under the curve to the right. Okay, but we have a standard deviation of 3.5. Remember those equations? We got everything we need to know right now. Okay. Okay, so the question might be a couple things here. Here's three types of questions. Okay, really two. Let's go with two. The customer says they want it in 42 days. What's the probability of not blowing through 42 days? That's the area under the curve to 42 days. Okay, so let's use our knowledge before we go forward with that too much further. Okay, before we go too much further with that. Okay, mark on our chart here. So I suppose I have to draw a bigger chart. Darn it, I didn't want to have to get involved with this at this point. Okay, so I can just draw it here. Okay, so our chart, you should be thinking the whole time through, critically thinking here. We have 38. We want 42. What's our standard deviation? 3.5. All right, so let's just take 3.5 and add it to 38. 41.5 is one standard deviation above, right? So we're a little bit beyond one standard deviation above. We're at 42, not 41.5. How much of the curve, okay, we're going to spitball it here, okay? So if we just rough it out really fast, you're sitting at the conference table in a meeting, okay, what's the probability of hitting at 42? Well, it's a little bit more than 41.5. Well, if 41.5 is one standard deviation above there, okay, this is how we're going to use geometry all day long, okay? So we know 68% lies between here. That means 32% on this side, okay? So the probability at 41.5 is going to be 50%. That's all this area down here left, right? And what goes up 32%? We're going to add 32. So we're about a little bit more than 82% sure. All right. That's why we use the empirical model, because you can slice and dice it rough. It's a rough cut as to what you're doing. All right. Not that you can read that. Hold on. Let me change my font. So 50 plus 32 is 82%. Okay. Excuse me. Not going to take that out. I'm not going to go edit out my coffin. Nope. All right. 82%. So we're a little bit above that, 83, 84, 85. Okay, so you're already pre-checking your numbers here. Okay, but let's really go through it the slow way. No, let's do the fast way. What formula do we need here? All we need is norm dot dist of the point we're interested in is 42. The mean is 38. Standard deviation of, what did I say? What did we figure out? 3.45. 3.5? Yeah, I'm just going to rough it out at 3.5. Okay? Oh, and I forgot. We have to run true. 3.5. And we always have to put the true in there. Okay, let's actually calculate that. Smart people equals norm dot dist of 42 is our point of interest. 38 is our average. 3.5, kind of cheating. I'm going to use 3.45. 3.45 and true. Spell everything right. Get them in the right order. Bang. What did I tell you? We have a little bit more than 82%. We have 87%. Okay? Right? Oh, but you say, that's cool. All right? It's cool or it's not. Only policy at the company is going to tell us whether that's good or not, right? How do we know? All right? So you have to have some kind of rubrics or criteria to be working with to tell us whether 87.7% rounding is good or bad. All right? But let's say the company expects us always to quote at 95% confidence that we're going to hit the date. So here's where the other formula comes into play. Okay? We need equals norm dot s dot inverse. Remember I told you we need inverse. Whoop, getting crazy here. 0.95. Okay, so what is the z? You got to remember what comes out of these equations here. So equals norm dot s dot inverse. Whoops, inverse of 0.95. The z is 1.64. Okay, so what we know z all day long is equal to, this is going to be what we're after. We're trying to figure out how many days. We know this mean and we know the standard deviation. Let's solve. Okay, so the point of interest is equal to z times the standard, a little dot there, times the standard deviation plus your mean is equal to 1.64 times standard deviation was 3.45-ish plus the mean was 38, right? Did I use 38 or 39? 38, right? Just do it. Okay, so go in and equals norm dot s dot in. No. What am I saying? No, I'm just calculating it. It's late. Don't laugh. It's late. So we're going to actually use the numbers. It's equal to the z. Did I actually calculate 3.45? Where did I get that? 3.45. I'm going to grab it from way up here. I know it's a little crazy. I'm not labeling things. It's late at night. I'm trying to help you out here. Okay, that plus 38. Okay, so wait for it. Drum roll, please. This is going to be the number of days associated with 95% is equal to 43. It's only a day 0.67 more. Okay, so we were pretty close. What does that say? It says we're on a part of the curve, Control Z. We're on a part of the curve that's fairly steep. I'm not going to get into it too much, but here's your curve, all right? And it says that by adding a little skosh there, see? We added a little skosh here. This was our 42, and we came out at 40, what did I say? 43, got to write it, 43.7. So a day, almost 2 days later, about 1.75 days, all right, gave us the jump from 87% to 95%. Okay, all right. Boom, you've got it. All right, we're pushing the numbers around, and this is how you learn statistics. So it's almost a little bit like a culture around this about pushing numbers around, and then everything starts making sense. Okay, so what do you want to know? You want to know, what exactly do I need to know? You know it. That's the project or the sample out of out of out of the book. You could go to the book and you could have learned all that right from the book, but you've got me here to help you with it. Okay. So what would be interesting, hint, hint, is if we improved, follow me on this, if we improve, we're always about constant improvement at this company. What if we change, I have to look it up here. What if we improved, follow me on this, activity C is now up here, activity C is now 3, 5, 13. Optimistic, nominal, pessimistic. What if F we're improving, okay? So F down here, what if that improved instead of 7, 8, or 9, 7, 8, 9er? What if you go to 3, 4, 5 on that, on F, okay? What if we do that? There you go. Set it up thinking about it. Take the problem that we just came from and talk about this. Think about what happens if these two things improve. What is the new critical path? And i.e., how much time does it take to get through there? What is the probability of finishing the project on time at the expected value of the new network? Okay, so if you quoted the actual expected value to your customer, what's the probability of hitting that, right? And how many days is associated with 92% probability? This is your company policy. Think about that. I want to keep this short and sweet. You've got everything you need to know for tomorrow, which is almost today. It's 11 o'clock tonight, right? So if you follow this and then follow the earlier part of what I just said, then you should be able to handle what we're going to see tomorrow, all right? So have a good evening, and we'll see you at the quiz, or rather the final first part tomorrow.